My name's Martin Wimpress. I lead DevRel and community at Slim.AI, and today I'm going to be sharing 5 best practices that you can start using today to better secure your production-ready containers. So first of all, we'll just introduce Slim.AI very briefly. So Slim.AI was created to give developers the power to build and build safer cloud-native applications with less friction. It's built on top of our open source, Docker Slim, and the Slim SaaS platform allows developers to optimize their containers, reducing both the overall size and the attack surface, or vulnerability count, depending on how you want to measure that. And by increasing the efficiency and decreasing the attack surfaces, Slim.AI ensures that you're only shipping into production what you need. So that's the quick pitch. Let's get into it. So I'm going to be introducing a sample application, and then we're going to look at some container best practice ahead of, using several techniques that focus on where it impacts security. And you should also understand exactly what you're shipping to production. So I'll introduce some tools you can start using today to help with that. Then we'll make an objective decision on what the best base image is for the application I'm going to use today. And finally, we'll harden the container image using Docker Slim to significantly reduce the attack surface. So the sort of too long didn't watch is basically this. So we're going to go from the example 1 there to the second example. Now, vulnerability count alone isn't like the be-all and end-all of assessing the security of your container images. I think there's another talk later today at 3 o'clock. I think it's like CVE, recovering from CVE shock or something like that. I think that's going to get in some more of the nuance around looking at CVEs. And also the container image sizes I'm going to be quoting today are their uncompressed sizes. So let's take a look at the base images we're going to use. So we're going to use a Python example. It's a very simple Python Flask application that implements an even simpler RESTful API. The app is just for illustrative purposes. It's really unimportant. We could have done this with Node or any other language or framework. And what we're going to do is we're going to containerize this application using 4 different base images and differing container image composition techniques. So we'll just look at one of the Docker files, sort of see where we're starting from. So this is one of the Docker files of the selection that I've got today, and it adheres to just best practice for container images. So it uses an official Python base image. We've defined our working directory for our app. It has good layer construction to minimize cache invalidation and optimize build performance. Files are only copied in as required. A port is exposed, which is helpful for Docker Slim. I'll talk about that a bit later. And it uses an entry point for proper signal handling. But there are a few things here that specifically help with container security, so let's just take a quick look at some of those. If you don't specify a user in your Docker file, your app will run as root. And nobody is an unprivileged system account, and that's available by default in Debian and Ubuntu and RHEL, Alpine, Distroless, and the list goes on. And the purpose of the nobody account is to run things that are intended that don't need any special permissions, basically. So it's usually reserved for services, so that if they do get compromised, the would-be attacker has minimal access or impact on the rest of the system. By contrast, if your app is running as root, the would-be attacker potentially has complete access to the container and any additional utilities that are inside that container image, and we'll talk about that a bit later. So, if I can talk about it now. So some of those things, tools and utilities that are shipped inside the container that the attacker could then potentially use to disrupt your infrastructure and operations. So, you're probably familiar with the concept of pinning. So we're going to choose a base image and pin it to a particular version. You'll see a number of tutorials for newcomers that suggest pinning to the latest tag because it's easy. However, containers are meant to be ephemeral, and we all know what that means. And using the latest tag means that there isn't a single source of truth for your container's bill of materials. resulting in your container getting whatever is the most recently updated version. So new revisions to the latest tag can introduce major version bumps to the system and the languages that go alongside it. And that can often be a flag day, which introduces breaking changes. So pinning a specific major and minor version to your Docker file is a trade-off. You're choosing not to automatically receive system and language upgrades via the update mechanism. But most DevSecOps teams prefer to employ security scanning as a way to control the updates rather than dealing with the unpredictability that comes with container build and runtime failures. So we'll now look at how specifying a base image can be helpful. So avoiding apt-get upgrade and the equivalents in Docker files was considered best practice, and in the majority of cases this is not good advice. Base images from vendors and large projects are frequently updated using the same tag, and those tags updates using the same tags usually include critical bug fixes and security updates. However, there can often be delays between those updates being published in the package repositories versus the base images being published to the registries. So relying on the base image alone is not sufficient. Even images blessed by and maintained by large companies and organizations with plenty of resources. So if you now imagine an open source project maintained by someone in their spare time, these delays can be significant. If you pin a stable base image, as we just discussed, the updates that you apply are purely focused on security fixes and severe bug fixes. So you can safely apply those system updates at build time without introducing unexpected upgrades that may introduce breaking changes. But you do need to be sure that you're actually applying the latest updates. So Docker builds can be slow, so we use layer caching to reuse the build steps from prior builds to speed up the current one. And whilst this does improve build performance, there's a potential downside which can lead to insecure images. For most Dockerfile commands, if the text of the command itself hasn't changed, then the previously cached layer will be reused in the current build. So when you're relying on caching, those apt-get, install, update commands, run commands, can potentially add old, possibly insecure packages into your images, even after the distro vendor has released security updates. So you're going to want to bypass layer caching on some occasions. And you can do this with Docker build, with --pull and --no cache. Pull, always pulling the latest version of the base image, and no cache ensures that additional layers in the Docker file get rebuilt from scratch instead of relying on the caches. So what you're going to want is two build processes. A normal image build process that happens when new code is released, and then every night a rebuild of your container image from scratch using Docker build --pull --no cache to ensure you've got the latest security updates. So with those steps, we've basically adhered to sort of container best practice, but what's actually inside our containers. So you should definitely be performing vulnerability scans and generating SBOMs of your production containers in your image build pipelines. And review the results. These are extremely useful tools that can give you good insight into what's in your container and what you're shipping to production and what your potential exposure is. Docker has integrated vulnerability and SBOM scanners. Docker Scan is powered by Sneak, and Docker SBOM is powered by Sift. But for the purposes of this presentation, I use the Slim SaaS platform, which has Gripe, Trivy, and Sneak integrated. Gripe, Sneak, Trivy, and Claire are all useful tools for assessing your containers, and I recommend you give them all a try. They're all tools you can download and integrate into your build pipelines. They're all open source. So using the Slim SaaS and more recently the Slim.AI Docker extension, I can demystify the containers and really get to know what's inside them. So knowing what's inside your container is critical to securing your software supply chain. The Slim platform lifts the veil on the internal so you can analyze, optimize, and compare the changes before deploying cloud-native apps. So let's use container scanning and analysis to determine what the best base image would be for our example application. The regular official Python latest image is built from Debian 11 and it weighs in at 921 megabytes, but smaller starting points are available. I'll containerize the app using 4 different base images. We're going to use the official Python image, which is based on Alpine 3.16. The official Python image using their Slim version based on Debian 11. That's not a relation to us. You'll quite often see Slim variations of projects. We'll use a distroless multi-stage build, and we'll use an Ubuntu 22.04 base image, which doesn't include Python by default, so it has to be installed via a Docker file run command. So sometimes it is necessary to install additional applications to facilitate the successful build of your container images. As I said, the Ubuntu base image doesn't include Python, so that needs to be installed via apt-get. The default options for system package installation in Debian, Ubuntu, and RHEL-based distros is to install the recommended packages, which can result in much bigger images than you actually need, and therefore more software in your images that you need, and greater attack surface. So that 921 megabyte Python latest base image is a good example of sort of package excess. So what you need to do is when you install system packages is avoid installing the recommended packages. Here are a couple of examples for Ubuntu and RHEL that install Python 3 but without the unnecessary recommended packages. And in that Ubuntu example, that reduced my container image size by approximately 300 megabytes. So we're going to build the app on each of these base images and see how the final sizes stack up. So here's the results. I was pleased to see other people using emoji in their presentations earlier. The images all include Python, our example application, and its dependencies, which is 11 packages installed via pip. So the adage goes that smaller is safer, and the smaller image size should correspond to fewer packages, and that should result in fewer vulnerabilities. So we can check that. So let's remind myself of the results. Okay, so we've got quite the spread there. Alpine clearly the smallest image, then distroless, then Ubuntu, and then the one built with the Python project Debian-based image. So these are the vulnerability assessments at a high level, and there's no denying that the Alpine results are excellent. The Python image based on Debian 11 is not looking so great, however, with 82 vulnerabilities, of which 1 is critical and 11 are high. These are all in system packages installed via apt, none of the pip packages. And that's something that we can get from those vulnerability assessments and also the SBOM analysis. Distroless, in this case for Python, is also based on Debian 11. I found it difficult to expose that without using our tools to actually go and poke around inside the container and get all of the analysis results to tell me what it was actually built on. And that was useful because another complexity of distroless is I had to make sure I was using the same distro in my multi-stage steps to ensure ABI compatibility with the rest of the runtime. So our tools really helped me figure out I needed Debian 11 with Python 3.9. So that has 47 vulnerabilities. 3 of those are critical and 5 are high. And again, these are all in system packages installed via apt. So with distroless, this is also a bit more tricky to mitigate because unlike traditional Debian-based images, there's no apt-get to install the latest updates. It can be worked around, but it is non-trivial. And that brings us to Ubuntu, which is where? Second on the list, okay. These numbers change every time I do this presentation, so I have to check. And it's another reference why you need to have this in your pipelines, because these numbers will go up and down over time. So I reran these this morning. So it's the third largest container image, which is interesting because the last time I did this, it was the largest. But it's got the second best vulnerability assessment, with no critical or high vulnerabilities, just 3 medium and 13 low risk and 8 negligible, which makes up the balance. So why is this? Because Ubuntu is derived from Debian, right? Well, Ubuntu is a commercially backed Linux distro with a full-time security team, and it has SLAs to mitigate vulnerabilities for their customers, which includes mitigating all critical and high vulnerabilities for the supported lifetime of the distribution. Debian is a community-maintained project, and while many Debian contributors, including myself, do fix security issues in Debian, it simply cannot provide the same level of commitment to security as the commercially backed Linux distro vendors such as Canonical, Red Hat, and SUSE do. So the Python image, which is based on Debian 11, is approximately the same size as the Ubuntu image, but has over 3 times the number of vulnerabilities. And in fact, 20 of the CVEs in that Python image based on Debian 11 are marked as won't fix, along with 15 in the distroless container image. These are known vulnerabilities that the Debian project will not fix in Debian 11, and therefore will not be fixed in any distroless or other container image based on Debian 11. So, based on this, Alpine is our clear winner, right? Sadly not. So, Python and Node and some other languages can result in significantly slower build times and introduce runtime bugs and unexpected behavior. This could be a talk in its own right, but in simple terms, this is due to the differences in muscle used in Alpine as opposed to glibc used in most other distributions. Personally, I don't recommend using Alpine for Python apps. I know there are people that advocate for the same from the Node community, but it can be great for Go and Rust. But what if? What if I could have the low complexity of maintaining Ubuntu-based containers and the security profile of Alpine? And what if I could make containers smaller than Alpine? So let's try that. So we use the terms slim, minify, harden, optimize interchangeably to describe the act of reducing the container image size and hardening and reducing the vulnerability count. So Docker Slim is free and open source. It's available on GitHub. It's a single Go binary. Both Docker Slim and the Slim SAS can automatically optimize your containers. So don't change anything in your container image and minify it by up to 30 times, making it more secure by reducing the attack surface of the container. Docker Slim has been used with, there's a big long list here, Node.js, Python, Ruby, Java, Golang, Rust, Elixir, R, and PHP, and it says, and many others, along with base images built on Ubuntu, Debian, CentOS, Alpine, Distroless, and again, along with many others. We have extensive examples in the Docker Slim GitHub organization. But when we say this, we always get asked how Docker Slim works, so let's try and summarize that in 1 minute or less. So Docker Slim optimizes container images by understanding what your application actually needs in order to run using various analysis techniques, including static and dynamic tracing. Now, I heard mention of eBPF earlier. Docker Slim was created 7 years ago, so some of that analysis is using syscall tracing, ptrace, library loading analysis, but we've got prototypes built with eBPF, which we're working on. So Docker Slim will basically throw away what the container doesn't need, and it does this by creating a single layer image, which is composed of only those files from the original container that were actually required by your application. So you can understand the container image before and after you optimize using the Slim SAS and the Docker Slim extension. It's deep introspection visual analysis tools of what's in your container, and you can do side-by-side diffs, basically, diffs of the whole container, or just the metadata. And it will show you exactly how the container image was changed. And there are a number of benefits to slimming containers. If you're familiar with no code from Kelsey Hightower, you should only ship into production. Ship no code, I think, is one of the mantras. So only ship into production what your app requires. So slim containers can be up to 30 times smaller, particularly with multi-gigabyte container images from sort of the AI/ML space. Slim container images are faster to deploy due to their lower size and faster to start due to having fewer files. They can be less expensive to store and transfer, and the slimmer containers reduce your attack surface. One of the things we noticed, we prepared a report last year. It's called What We Discovered, Analyzing the Top 100 Public Container Images, and we're in the process of updating that report for this year and expanding the number of containers that we're looking at. And it showed an increasing trend of dev, test, QA, and infrastructure tooling being left inside production-ready container images that are publicly posted. So a lot of the stuff you may well be using in your infrastructure. So unused shells, interpreters, tools, and utilities left in your container images can be used against your infrastructure to disrupt your operations if a container is compromised. Someone lands inside a well-instrumented container, maybe they've got Kubernetes controls in there, even things like curl and netcat and what have you can be used quite effectively to sort of island hop. So let's take a look at the slimmed containers. So all of those container images are being minified with Docker Slim. So these are the results. Let's just take a quick look. So Alpine is down 3 times from 60 megs to 19. Distroless down from 72 to 21. The Python image down from 159 to 23, and the Ubuntu image down to 25 megabytes, and the corresponding reduction sizes there. So in most cases, there are significant reductions to be had slimming any container image, regardless of the build technique or base images used. In our examples here, we see between 3 and 7 times. Yes, that's close enough, 6.8, that'll do. Which is quite modest, actually, because we, as I say, we gave us our best starting point by following best practice up front. And we typically see 10 to 30 times size reductions for complex applications. And our slim Ubuntu-based image is now just 6 megabytes larger than the slimmed Alpine image, but with none of the compatibility concerns, and it's 35 megabytes smaller than the unoptimized Alpine image. But has slimming also improved the vulnerability assessment? So let's find out. So analyzing if vulnerable components exist in slim containers is currently a semi-manual task, but we are working on fully automating this. That said, it only takes a few minutes, and that's at most, to use either the Slim SAS or the Slim Docker extension to search for the vulnerable components and confirm that they're no longer present in the Slim variants. Like I say, that pipeline and reporting is going to be fully automated soon. And we've already confirmed that that Ubuntu-based image had no critical or high-risk vulnerabilities. But there were 3 medium-risk vulnerabilities, and those were in libsqlite, Perl base, and zlib. And it took a few seconds to confirm that none of those components were in the slimmed image, because these are components that are not used by our application. And again, using the SAS platform, it only took a few more moments to confirm that all of the remaining low-risk vulnerabilities have also been removed by that minification process. So the answer is yes, we can have our cake and eat it too. We have an Ubuntu-based image with no known vulnerabilities of a comparable size to the slimmed Alpine image, but with none of the potential complexity of working with Alpine. So this analysis shows that, in this case, Ubuntu is the best base image for our example application. So let's just take a look at what we've covered. Following container best practice will set you up for success. Always run internet-facing apps and services using unprivileged user accounts. Pin your base images. Use stable base images and apply your updates at build time. Be mindful of layer caching. Potentially introducing insecure packages into your container images. Container scanning and analysis are essential to fully understand what they're fully understanding, to fully understand what's inside your container. Some of this, I haven't been able to show it live. If you want to see how any of this stuff works, I've got it all here. Catch me in a break and I'm happy to go through. I've got all of the data that supports all of this and we can dig into it. Quite happy for anyone to sort of poke holes in any of my findings here. Don't install the recommended packages to help keep your images slim and secure. Linux vendors have security SLAs. And so assess your base image options. You know, if you've got a language framework that you're using, choose the most secure option. You can use our platform to actually just connect to their public registry and do a security audit. Just like that takes a few seconds. And maybe you'll learn that actually composing your own base image gives you a better security posture than using something from one of the upstream projects. And you can slim just about any kind of container image, including those based on Alpine and distroless. So if you're looking at a need to make container images smaller, for whatever reason that might be, and you've already got, say, something built on one of the Red Hat distros or something from SUSE or Ubuntu, and you're looking to switch to Alpine, the whole point of Docker Slim is to not change your build processes, just add a post-processing step that makes them smaller at the end. And slimming removes vulnerabilities and reduces your attack surface. So that was a few more than 5, and you're welcome. I think we're running a bit over, so thank you for listening. I hope you picked up a few tips to help improve the security of your containers. We invite you to give the Slim SaaS and the Slim Docker extension a try. Both are free to use. And also take Docker Slim for a spin. That's also free to use. It's on GitHub. If you have any follow-up questions, then you can ask me over the next 2 days or join our Discord, ask in there. Or you can follow us on Twitter at SlimDevOps and ask us there. Have we got time for questions, or do I need to move on?
We've got one question time.
One question. Make it a good one. Right, your hand was first up at the back there.
Do you have some metrics or data? How reliable is Docker Slim? You say it removes things it doesn't use, but can it over-remove and the application breaks?
Yes, it can. But there are a number of techniques you can use to prevent that from happening. So if you've got integration tests, then what Docker Slim does is it actually launches your application inside a container and observes it running. You can instruct it what to do. By default, it will just do some basic crawling. It will look at the exposed port and crawl it. We had a presentation from somebody from Postman earlier. You could export your API map from Postman and give that as an input to Docker Slim, and it will know what all the endpoints are to go and discover to give you better coverage of exercising the app. Or integration tests. Tell Docker Slim to run your integration tests just as you would in the composition part, and you can get the best outcome that way. And if you've got static assets, they're in a particular location, you can just instruct it. Everything here I want, regardless, just always include these things. So there are techniques around it, and we're improving it all the time. We've started adding sort of language and framework, ecosystem-related hints to the process. I mean, this is in the Slim SaaS platform, so you can say, this is a front-end application built with Nuxt.js, and it will know there are certain additional things it needs to do to sort of fully discover that. And we've got things for command line apps, server apps, and just some starting points, and we're building that out over time. Okay, any other questions? Find me later.
All right, thank you very much. A round of applause.